Attention is all you need. Have you ever wondered if we could build a smarter AI without all the complex parts? Well, that's exactly what this paper does. It introduces the transformer, a model that ditches the usual recurrent and convolutional networks. Instead, it relies entirely on attention mechanisms. This makes it faster to train and more parallelizable. In tests, it smashed records in machine translation, achieving a 28.4 BLEU score for English to German and 41.0 for English to French. And get this, it did all that with way less training time and cost. This isn't just an improvement, it's a game changer for how we handle sequences. For years, recurrent neural networks like LSTMs have been the go-to for tasks like language modeling and translation. They've been pushed to their limits with constant improvements. But here's the thing. What if we could break free from that complexity? This paper challenges the status quo by exploring a simpler, more efficient approach. Why are recurrent models so slow? They process sequences step by step, like reading a book one word at a time. Each step depends on the previous one, making it impossible to parallelize. This becomes a huge bottleneck with long sequences, limiting how much data you can train on at once. Some tricks have improved efficiency, but the core issue of sequential computation remains a major roadblock. Attention mechanisms are game changers. They let models focus on important parts of a sequence, no matter how far apart they are. But here's the catch. Most models still use attention with recurrent networks. So are we missing out on something bigger? This changes everything. The transformer ditches recurrence entirely and relies only on attention. This allows massive parallelization, slashing training time. Imagine training a state-of-the-art translation model in just 12 hours on 8 GPUs. That's the power of this new architecture. Other models like Extended Neural GPU, ByteNet, and conv-S2S also aim to reduce sequential computation using convolutional networks. They compute in parallel, but relating distant positions still requires more operations as the distance grows. The transformer fixes this with a constant number of operations, though it averages attention weights, which we'll see how it handles with multi-head attention later. Self-attention is like a model, looking at all parts of a sequence at once to understand its meaning. It's been super effective in tasks like reading comprehension and summarization, helping models grasp context without getting lost in the details. End-to-end memory networks use recurrent attention and perform well in simple tasks like question answering, but they still have that recurrent element holding them back. Here's the kicker. The transformer is the first model to rely entirely on self-attention. No RNNs or convolutions. This is a bold move, and in the next parts, we'll dive into why self-attention is such a big deal and how it outperforms older models. Most top models use an encoder-decoder setup. The encoder takes an input sequence and converts it into a continuous representation. Then, the decoder generates the output step by step using what it has already produced. It's autoregressive, meaning each new step depends on the previous ones, building the output gradually. The transformer keeps this encoder-decoder structure but replaces the usual components with stacked self-attention and fully connected layers. This is shown in the figure, where the left side is the encoder and the right is the decoder, all designed for maximum efficiency. The encoder has 6 identical layers, each with 2 sublayers. First, there's multi-head self-attention, which we'll explore in detail. Second, a simple position-wise layer that processes the data further. This setup ensures robust feature extraction without the slowdown of recurrence. Ever wondered how the transformer model actually processes information? This diagram shows the flow from input to output, with components like multi-head attention and feed-forward networks stacked together. It's like a factory assembly line where each part adds a new layer of understanding, using techniques like normalization and residual connections to keep everything stable and efficient. This setup allows the model to handle complex tasks without getting bogged down by sequential processing, making it super fast and powerful. Here's the kicker. The model starts with input and output embeddings, where the output is shifted right to predict the next word. Think of it as a smart guessing game, where the model uses what it already knows to figure out what comes next, all while maintaining context through positional encoding. This clever trick ensures that predictions are made step by step, building on previous outputs without peeking ahead. This figure illustrates the entire transformer architecture, showing how the encoder and decoder work together in a neat, stacked design. It's the blueprint for a model that ditches recurrence and relies purely on attention, making it a game changer for tasks like translation by handling long-range dependencies effortlessly. Why add residual connections and layer normalization? It's all about stability and learning efficiency. Imagine building a tower where each block is secured with extra support. Residual connections let information flow smoothly without getting lost, and normalization keeps the data in check. This means the model can train deeper networks without the usual hiccups, using a fixed dimension of 512 to keep everything consistent and scalable. Now the decoder takes it up a notch with an extra layer for multi-head attention over the encoder's output. But here's the twist. It uses masking to prevent cheating by only looking at past positions. This ensures that when predicting the next word, it only relies on what's already been generated, making the process auto-regressive and accurate. It's like having a strict rule in a puzzle game. No peeking at the answers ahead of time. What exactly is attention in AI? It's a mechanism that lets a model focus on the most important parts of the input. Picture this. You have a query, keys, and values, like searching for a book in a library. The query is your question, keys are the book titles, and values are the actual content. The model calculates weights to decide which books are relevant, then combines their content to produce the output. This weighted sum approach allows it to prioritize information dynamically, making decisions smarter and more context-aware. Diving into scaled dot product attention, this is the transformer's secret sauce for efficiency. It takes queries and keys of the same dimension, computes their dot products, and scales them down to avoid huge values that could mess up training. This method is fast and parallelizable, unlike older approaches, and it's key to how the model handles multiple pieces of information at once without slowing down.
We are Genapad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genapad.com.
All right, check this out. On the left, we have scaled dot product attention. It's like the brain's way of focusing on what's important by comparing queries and keys, then scaling things down to avoid chaos. And on the right, multi-head attention is a game changer. It runs multiple attention layers at the same time, letting the model see different perspectives all at once. Why does this matter? Because it makes the model smarter and faster, handling complex tasks without getting bogged down. Here's how it works. You take a query and match it with all the keys, then divide by the square root of the key dimension to keep things stable. Apply a softmax to get weights, and bam, you've got the focus on the right values. This scaling is crucial. Without it, things could go haywire with huge numbers messing up the gradients. Ever wondered how this scales up in real life? Instead of handling one query at a time, we pack them all into a matrix Q. Same for keys and values, matrices K and V. This lets us compute attention in one big, efficient batch. Think of it like processing a whole crowd instead of one person at a time, making everything lightning fast. So the formula is attention equals softmax of Q times K transpose divided by the scaling factor, then multiplied by V. This is the heart of dot product attention. Simple, elegant, and super quick to run on modern hardware. Now there are two main types of attention, additive and dot product. Dot product is what we use here, and it's basically the same but with that scaling trick. Additive attention uses a neural network with a hidden layer, which sounds fancy but is slower. Why? Because dot product leverages super-optimized matrix math, making it a speed demon in practice. This changes everything for training efficiency. Here's the kicker. For small dimensions, both methods are similar, but when dimensions get large, dot product without scaling falls apart. The dot products blow up, pushing the softmax into areas with tiny gradients. Basically, learning grinds to a halt. To fix this, we scale by the square root of the dimension, keeping everything smooth and stable. It's a simple tweak with huge impact. Instead of using one big attention head, multi-head attention splits the queries, keys, and values into multiple groups with different learned projections. Each group does its own attention in parallel, and then we combine them all. This allows the model to focus on various aspects simultaneously, like having a team of experts each looking at a different part of the problem. Why is this so powerful? Multi-head attention lets the model capture information from different subspaces all at once. With a single head, it's like averaging everything together, which can hide important details. But with multiple heads, it's a symphony of focus, making the model much more capable. To understand why scaling is needed, imagine the query and key components as random variables with mean 0 and variance 1. Their dot product then has a variance equal to the dimension size. When that dimension is large, the dot product values can get huge, messing up the softmax. Scaling by the square root of the dimension keeps the variance in check, ensuring stable training. Ever wondered how the transformer handles multiple perspectives at once? It uses multi-head attention, which combines several attention heads into one powerful mechanism. Each head processes queries, keys, and values independently, and then they're all concatenated and projected to give a richer understanding of the data. Here's the kicker. Each head has its own set of learnable matrices that project the inputs into smaller dimensions. This splitting allows the model to focus on different aspects simultaneously without blowing up the computational cost. Why does this matter? In their setup, they use 8 parallel heads with 64 dimensions each. This design keeps the total computation similar to a single large head, but it captures way more diverse patterns. It's like having a team of experts working in parallel instead of one person doing all the work. So, how does the transformer actually apply multi-head attention? It uses it in 3 clever ways to handle different parts of the translation process. First, in encoder-decoder attention, the decoder queries the encoder's output to focus on relevant parts of the input sequence. This is crucial for tasks like translation, where each output word needs to consider the entire input. Second, self-attention in the encoder lets each position attend to all others in the same layer, building a comprehensive representation. Third, self-attention in the decoder is restricted to prevent peaking at future tokens, maintaining the autoregressive property. They achieve this by masking out illegal connections in the softmax step. But attention isn't the whole story. After the attention layers, the transformer adds a feed-forward network to each position. This network applies the same 2 linear transformations with a ReLU activation in between, processing each token independently to add nonlinearity and depth. The formula might look complex, but think of it as a simple neural network step that refines the information. It uses max 0x for ReLU to introduce nonlinearity helping the model learn more complex patterns. Here's the interesting part. Even though this network is applied identically to every position, each layer in the encoder or decoder has its own set of parameters. This allows the model to evolve its understanding as data moves through the layers. With an input and output size of 512 and a hidden layer of 2048, it's designed to handle substantial computations efficiently. Now, let's talk about how the transformer handles tokens. It uses learned embeddings to convert words into vectors, and a softmax function to predict the next token. A smart trick here is sharing weights between the embedding and pre-softmax layers, which reduces parameters and improves consistency. They also scale the embeddings by the square root of the dimension to stabilize training. Since the transformer has no recurrence or convolution, how does it understand the order of words? It uses positional encodings added to the input embeddings. This injects information about token positions, allowing the model to process sequences without relying on sequential steps. Ever wondered how different neural network layers stack up in terms of efficiency? Let's dive into Table 1, which compares maximum path lengths, per layer complexity, and the minimum sequential operations for self-attention, recurrent, and convolutional layers. This table is crucial because it shows why self-attention is a game changer. It handles long sequences with constant operations, making it super fast and parallelizable compared to the slow, sequential nature of recurrent layers. At the bottom of the encoder and decoder stacks, positional encodings come into play. They have the same dimension as the embeddings, so they can be added together seamlessly. Why does this matter? It helps the model understand the order of words without relying on recurrence, and there are many ways to do this, either learned or fixed. In this paper, the authors use sine and cosine functions with different frequencies for positional encoding. This choice isn't random. It's designed to make the model smart about relative positions, allowing it to generalize better. Here's the formula for positional encoding. It uses sine for even dimensions and cosine for odd dimensions, with frequencies that decrease geometrically. This setup creates a unique pattern for each position, helping the model track where words are in a sequence without any recurrence. Each dimension of the positional encoding corresponds to a sinusoid wave, with wavelengths forming a geometric progression. Why is this so clever? The authors hypothesized that this allows the model to easily learn relative positions. For any fixed offset, the encoding can be expressed as a linear function, making it simple for the model to attend to nearby or distant words efficiently. The team also tested learned positional embeddings and found they performed almost identically to the sinusoidal version. But here's the kicker. They stuck with sinusoids because they enable the model to handle sequences longer than those seen in training. This means better extrapolation and more robust performance on real-world data. Why self-attention? In this section, we compare self-attention layers to recurrent and convolutional layers for processing sequences. The goal is to map one sequence to another, like in translation tasks. The authors highlight 3 key factors that make self-attention stand out: computational complexity, parallelization potential, and how it handles long-range dependencies. First up is total computational complexity per layer. Another big one is how much computation can be parallelized, measured by the minimum sequential operations required. Self-attention shines here because it processes everything in parallel, unlike recurrent layers that are stuck in a sequential loop. The third factor is the path length for long-range dependencies. Learning these dependencies is tough in tasks like translation. Shorter paths between input and output positions make it easier. Self-attention excels by providing constant path lengths so signals don't have to travel far, enabling the model to capture relationships across the entire sequence effortlessly. As shown in Table 1, a self-attention layer connects all positions with a constant number of sequential operations, while recurrent layers need many more. In terms of speed, self-attention is faster when the sequence length is smaller than the representation dimension, which is common in machine translation. For very long sequences, self-attention can be restricted to a local neighborhood to stay efficient, making it versatile and powerful. Ever wondered how models handle long sequences without getting bogged down? This part hints at future research to reduce the path length to ON/R, potentially making processing even faster and more efficient. Stay tuned for what's next. Why do convolutions struggle with connecting all input and output positions? They need multiple layers, which can be slow and expensive. But here's the kicker. Separable convolutions cut complexity down, matching the efficiency of self-attention and feed-forward layers used in the transformer. This shows how the model's design outshines traditional methods for speed and performance. And here's a bonus. Self-attention makes models more interpretable. Imagine being able to see what the model focuses on, like peeking into its brain. Different attention heads learn unique tasks, often aligning with sentence structure, which could revolutionize how we understand AI decisions. Ready to dive into how this groundbreaking model was trained? This section breaks down the entire training process, from data handling to optimization. Let's get into the nitty-gritty of making the transformer learn effectively. First up, training data and batching. The model used the WMT 2014 datasets, 4.5 million sentences for English-German, and a massive 36 million for English-French. Sentences were encoded with byte pair encoding, creating a shared vocabulary to handle different languages efficiently. Batches were grouped by sequence length, ensuring each training batch had around 25,000 source and target tokens. This smart batching helps the model learn faster and more consistently. Now, let's talk hardware. The training ran on 8 NVIDIA P100 GPUs. For the base model, each step took just 0.4 seconds, totaling 100,000 steps over 12 hours. The bigger model, it needed 1.0 seconds per step and 300,000 steps, adding up to 3.5 days. This shows the scalability of the transformer, handling larger models with reasonable training times. Optimization is key to training success. The Atom Optimizer was used with specific parameters to fine-tune learning. But here's the cool part. The learning rate wasn't fixed. It increased linearly for the first 4,000 steps to warm up the model, then decreased based on the step number. This dynamic approach helps the model converge faster and avoid getting stuck. This formula controls the learning rate, starting low, peaking, and then tapering off. It's like easing into a workout to prevent injury. Smart, right? With a warm-up of 4,000 steps, this strategy ensures stable training from the get-go, making the model learn smoothly without overshooting. To prevent overfitting, the model uses 3 regularization techniques. Think of this as adding guardrails to keep training on track. Residual dropout is applied at 10% to sublayer outputs and embeddings. This randomly turns off some neurons during training, forcing the model to be robust and not rely too much on any single part. It's a simple trick that makes a huge difference in generalization. All right, let's dive into this table that's packed with some game-changing results. The transformer model is absolutely crushing it on BLEU scores for English to German and English to French translations. What's BLEU? Think of it as a score that measures how close the machine's translation is to a human's higher is better. And get this, the transformer does this with way less training cost. That means it's not just smarter, it's way more efficient. For instance, the big transformer model hits a BLEU of 28.4 for English-German and 41.0 for English-French, beating out older models like ByteNet and convs2s. The training cost is measured in flops. That's floating point operations, a way to gauge computational effort. The transformer's numbers are lower, showing it trains faster and cheaper. This isn't just a small win. It's a massive leap in AI efficiency. Why does this matter? Because it makes high-quality translation accessible without needing supercomputers for months on end. Now, here's a cool trick they use during training. Label smoothing. Imagine you're teaching a model, and instead of being 100% sure about every answer, you make it a bit uncertain with a value like 0.1. This might sound counterintuitive. It actually makes the model's confidence drop, so it's less overconfident. But here's the kicker. It improves accuracy and BLEU scores. Why? Because it prevents the model from getting too fixated on tiny details and helps it generalize better. So by embracing a little doubt, the transformer becomes more robust and reliable in real-world tasks. Let's talk about machine translation results. And wow, the transformer big model is a superstar. On the English to German task, it scores a BLEU of 28.4, which is over 2.0 points higher than the best previous models, even ensembles. What's an ensemble? It's like combining multiple models for a boost, but the transformer beats them all solo. And the training? Just 3.5 days on 8 GPUs. That's lightning fast compared to older methods. Even the base model, which is simpler, outperforms everything published before. And it does it for a fraction of the cost. This changes everything because it shows that attention mechanisms alone can achieve top-tier performance without the slow, sequential processing of older models. Switching to English to French, the transformer big model hits a BLEU score of 41.0, again beating all single models out there. But here's the real shocker. It does this with less than a quarter of the training cost of the previous state-of-the-art. They tweaked the dropout rate to 0.1 instead of 0.3 for this task. Dropout is like randomly turning off parts of the network during training to prevent overfitting. So by adjusting this, they made the model even more efficient. This isn't just about better scores. It's about making AI training affordable and scalable for everyone. How did they make these models so stable? For the base models, they averaged the last 5 checkpoints. Think of checkpoints as snapshots of the model during training. By averaging them, they smooth out any fluctuations and get a more reliable final model. For the big models, they used the last 20 checkpoints. Then, during inference, they used beam search with a beam size of 4 and a length penalty of 0.6. Beam search is like exploring multiple translation paths at once to pick the best one, and the length penalty encourages outputs that aren't too short or too long. They also set a maximum output length based on the input, but stop early if possible. These smart choices, tested on development sets, ensure the model delivers consistent, high-quality translations without wasting resources. This table sums up the whole story. It compares translation quality and training costs across different models. To estimate training cost, they multiplied training time by the number of GPUs and their computational power. This gives a clear picture of efficiency. The transformer stands out because it achieves top scores with minimal cost, proving that attention-based architectures are the future. Why does this table matter? It shows that you don't need massive computational budgets to get state-of-the-art results. This model is a game changer for making AI more accessible. Ever wondered what makes the transformer tick? In this section, they tweak different parts to see what's essential. They varied the base model and tested it on English to German translation using a development set. They used beam search, but didn't average checkpoints this time, focusing purely on the components. This is like taking apart a high-performance engine to see which parts boost power the most. By isolating changes, they can pinpoint exactly what drives the model's success. Here's where it gets interesting. They played with the number of attention heads and the dimensions of keys and values, all while keeping the total computation the same. Attention heads are like having multiple experts looking at the data from different angles. With too few heads, say, just one, performance drops by 0.9 BLEU. But with too many, it also suffers. Why? Because each head captures a different perspective, and there's a sweet spot where they work together without overlapping too much. This experiment shows that balance is key, not too little, not too much, for optimal performance. They used specific TFL OPS values for different GPUs like K80, K40, M40, and P100 to estimate computational power. TFL OPS measure how many calculations a GPU can handle per second. This helps standardize training cost comparisons across hardware, making the results fair and reproducible. It's like using the same ruler to measure everyone's height, ensuring that the efficiency gains they report are real and not just dependent on the machine. All right, let's dive into Table 3. This table is all about testing different versions of the transformer architecture. Ever wondered how tweaking things like the number of attention heads or the size of layers affects performance? Well, here's the kicker. It shows us exactly that. The metrics are from the English to German translation task, using perplexity and BLEU scores. Perplexity measures how confused the model is, with lower being better, and BLEU scores translation quality, with higher being better. But heads up, the perplexity here is per word piece, so don't compare it directly to other models that use per word measures. This table is crucial because it helps us see what makes the transformer tick and where we can optimize it for even better results. Now let's break down the data in this table. It's packed with numbers showing how different setups perform. For example, the base model has 65 million parameters and hits a BLEU score of 25.8. But check this out. When they increase the model size, like in the big version with 213 million parameters, the BLEU score jumps to 26.4. That's a solid improvement. Why does this matter? Bigger models often learn more complex patterns, but they also need more data and compute. Also, notice how dropout helps prevent overfitting, keeping the model from just memorizing the training data. And here's a fun fact. Using learned positional embeddings instead of sinusoidal ones gives nearly the same results, showing that both methods work well for handling word order. This table is like a cheat sheet for building efficient transformers, highlighting the trade-offs between size, speed, and accuracy. So what do we learn from rows B, C, D, and E in the table? In row B, when they shrink the attention key size, the model quality drops. This tells us that having a larger key size helps the model figure out which parts of the input to focus on. It's like trying to solve a puzzle with fewer clues. It just doesn't work as well. Then, in rows C and D, bigger models perform better, which makes sense because more parameters can capture more nuances. And dropout? It's a game changer for stopping overfitting, acting like a safety net during training. Finally, in row E, swapping sinusoidal positional encodings for learned ones gives almost identical results. This changes everything because it means we have flexibility in how we handle position without losing performance. These insights are key to understanding why the transformer is so powerful and how we can adapt it for different needs. We've reached the conclusion, and it's a big one. The transformer is the first model to ditch recurrent layers entirely and rely only on attention. Have you ever wondered if we could build a model without the slow sequential processing of RNNs? Well, this is it. By using multi-headed self-attention, it processes everything in parallel, making it super fast and efficient. This isn't just a small upgrade. It's a revolution in how we handle sequences like language. For translation, the transformer trains way faster than recurrent or convolutional models. On English to German and English to French tasks, it sets a new state-of-the-art. And here's the kicker. Its best model even beats all previous ensembles. Why does this matter? It means we're getting top-notch accuracy without the heavy computational cost, opening doors for more accessible AI tools. The future looks bright for attention-based models. The team plans to apply the transformer to other areas beyond text, like images, audio, and video. Imagine using this for video captioning or music generation. They also want to explore local attention mechanisms to handle huge inputs efficiently and make generation less sequential. This could lead to real-time AI applications that feel almost magical. If you're excited to try this out, the code is available on GitHub. Go ahead, experiment, and see what you can build. It's all open for you to dive in and contribute to the AI community. The authors give a shout out to colleagues for their helpful feedback and inspiration. It's a reminder that great ideas often come from collaboration and sharing knowledge.